Hello, welcome to this video. So this video is quite unlike many of the others I will do. This is a fairly relaxed kind of one. So I made this whilst doing an ASMR video, hence the dreaming thing. But this is just kind of like a video where I show how I would go about trying to work out something. So the question we have today is, we have the Earth, our good old friend. Let's actually let's make this larger. Let's make this as large as we can. So, we'll work with this for now. And we have the Sun. Here's a go from the Sun. And the Earth is orbiting around the Sun. And the Sun is clearly generating gravitational pull, which is pointing towards itself. So the force of gravity, or the acceleration, is acting this way, and the speed of the Earth is acting this way. And you might wonder, well, how can we show? So we want to show that the acceleration of the Earth due to the Sun will not cause its speed to change. Speed, or in other words, the magnitude of its velocity, to change. And that's what we're going to prove in this video. We can prove it today. Or depending when you're watching this video, if you're watching it at midnight, possibly tomorrow, depending on when you start counting tomorrow. Now you might think, if there's a force causing acceleration, an object will change its speed. It will speed up or slow down. And that'd be true if there was any component of the force along the direction it's moving in. But that's not really the case. The force is actually perpendicular to the velocity. It's at right angles, and so there's no component of the acceleration along the direction of the velocity. So we wouldn't expect the size of velocity, or the speed, in other words, of the Earth to change. Instead, since the acceleration is perpendicular to the direction of motion, or to the velocity, in this case gravity is causing a moment, if you like. It causes the trajectory to bend, or causes a moment. But can we prove that it will only cause a moment? Can we prove that the size of velocity won't change? Well, to do that, we're going to make use of something called the scalar product, to rephrase this more mathematically. So, essentially, if we have two vectors, so let's say A and B at some angle between each other, if they're perpendicular, so if the angle is 90 degrees, then we define something called the scalar product between them to be zero. For this video, I'm not really too bothered what the scalar product is, but this is just a consequence of how we define the scalar product. So we can rephrase our original geometrical question in a purely algebraic sense. So, we want to, if we just keep in mind our diagram, here, we want to show that if these vectors are perpendicular, so if the scalar product is 0, then the speed of the Earth, so the magnitude of V, is constant, or doesn't change with time. So, in other words, the derivative of the size of B with respect to time is 0. So, that's what we're going to try to show. We're going to essentially try to show that a scalar product of 0 here implies that d by dt of V is 0. We want to show that this is the case. Well, let's get about doing that. So, I'll just leave at the top what we're doing. We're going to show that if V plotted with A is 0, then d by dt of the size of V is 0. So let's go about doing that. Well, the first thing I note, really, is that by definition, acceleration, so this means by definition, when you have 3 parallel lines of 2, so it's equals, but it's true by definition. It's not an equation, it's just a definition. Acceleration is defined to be the rate of change of a velocity vector. Rate of change of velocity. So we can rewrite the scalar product being 0 as essentially saying that V dotted by d by dt of V is 0. That's just using our definition of acceleration. Now here we see we've got something multiplied by derivative of that thing, and that to me is screaming to use the product rule to in some way compactify this expression. Because if we use essentially the product rule, if we think of differentiating this, the product rule will give us this plus, which is twice of V times d by dt of V. So we can replace this with half of that, And this is a trick you often use in physics. If you see something times the derivative of that thing, you can use the product rule to compactify it into a simple expression. So we end up with, if I just draw this out clearly, we end up with saying that if this is true, then by definition, using my definition of the acceleration and the product rule, we have shown that this is also true. And now if we look at d by dt of, well, quite strictly we said a half of d by dt of v dot in v is 0, well, we could simplify that to d by dt of v dot v is 0. But using the scalar product, v dotted with v by definition is equal to the magnitude of v squared. And this is true by definition. It's true by the way that we define the scalar product. And so, we can conclude that this is true. So we've shown that the time derivative of the square of the speed is 0, but can we get that the time derivative of the speed is 0? Well, yes, we can, using the product rule once more. Because using the my good old friend, the product rule, and bearing in mind that the size of v squared is just v multiplied by v, this becomes that essentially 2 times v times d by dt of v is 0, and we can then just divide by 2 times the size of v, leaving us with d by dt of the size of v is 0. Which is what we want to prove, because this says that the speed is constant. But we can do better than that. So we've shown that the speed is constant, but can we show that the velocity should change? So we've shown now our original statement. We have proven we have proven that, but can we show that although the speed is constant, the direction velocity constant should change? So now, can we show that if this is 0, then our velocity does change? So d by dt of v cannot be 0. Well, we can do that very easily, because d by dt of v is a, so if a doesn't equal 0, then clearly d by dt of v can't equal 0. So if there's a force, there must be a change in the vector velocity, but providing that force is perpendicular to the velocity, there's no change in the speed of the object. So this was just a quick video, really, showing how I go about doing some calculation. I hope you've enjoyed it. I hope you got something out of it, and I hope to see you for another equation.